The formation of a neutron star is one of the final steps in the life cycle of a massive star. When a star that's much larger than our sun reaches the end of its life, it undergoes what's known as a supernova explosion. This occurs when the star has exhausted its nuclear fuel, causing the core to collapse under its own gravity. For most stars, the collapse halts at the formation of a white dwarf, but for stars above a certain mass threshold, the core continues to collapse even further. The protons and electrons within a star's core are forced together, creating neutrons through a process known as neutronization. This collapse is so powerful that the core is compressed to an extreme density, forming a neutron star, which is composed almost entirely of neutrons, thus the name. The structure of a neutron star is both fascinating and complex. At its heart lies an incredibly dense core, possibly containing a superfluid of neutrons. The exact nature of this core remains a subject of intense study, but it may include exotic forms of matter, such as quark matter or hyperons, particles heavier than neutrons. Surrounding this core is a mantle of degenerate neutron-rich matter, which extends to the star's surface. This surface, despite the star's extreme density, is only a few kilometers away from the core due to the compact nature of neutron stars, with diameters typically around 20 kilometers or so. The surface of a neutron star is a solid crust of atomic nuclei and electrons. This crust is only a few hundred meters thick, but it's immensely strong and rigid due to the intense gravitational forces at play. Neutron stars also possess incredibly powerful magnetic fields, much stronger than those found on Earth or even those in normal stars. These magnetic fields play a crucial role in many of the star's properties, including its radiation and interaction with surrounding matter. The density of neutron stars is their most defining characteristic. A typical neutron star contains about 1.4 times the mass of our sun, but it's compressed into a sphere with a radius of only around 10 to 15 kilometers sometimes. This results in a density so extreme that a single sugar cube-sized amount of neutron star material would weigh billions of tons. The pressure inside a neutron star is equally astounding, reaching levels far beyond anything that can be replicated on Earth. In the core, the pressure can be so great that matter behaves in ways that defy our conventional understanding of physics. These extreme conditions lead to other remarkable properties. Neutron stars are among the hottest objects in the universe when they are first formed, with surface temperatures reaching up to 1,000,000 degrees Kelvin. Although they cool over time, they remain hot and dense enough to radiate energy across the electromagnetic spectrum. The radiation emitted by neutron stars comes primarily in the form of X-rays and gamma rays due to their high temperatures and magnetic activity. This radiation can be detected by astronomers, providing key insights into their properties and behavior. A special class of neutron stars, known as pulsars, emit beams of radiation from their magnetic poles. neutron star rotation is another one of their fascinating features. Due to the conservation of angular momentum, when the core of a massive star collapses to form a neutron star, its rotation speeds up dramatically, similar to how a figure skater spins faster when they pull their arms in. So, as a result, as I alluded to earlier, neutron stars can rotate at astonishing speeds, with, again, some spinning as fast as several hundred rotations per second. Now, over time, these stars gradually slow down due to the emission of radiation and other energy losses, but even then, they still remain among the fastest spinning objects in the universe. The population of neutron stars in the universe is vast, though only a small fraction of them have actually been detected. Many neutron stars are isolated and emit very little radiation, making them difficult to observe. But neutron stars are often detected in binary systems, or as pulsars, where their unique properties make them stand out. Neutron stars are relatively close to Earth in astronomical terms, with some being located just a few thousand light years away, but they're scattered throughout galaxies, with the Milky Way alone potentially hosting millions of them. Binary neutron star systems are of particular interest to scientists. In these systems, two neutron stars orbit each other in close proximity, and their interactions can lead to fascinating phenomena. As the stars orbit, they lose energy in the form of gravitational waves, causing them to spiral closer together. When they finally merge, the collision releases an enormous amount of energy in the form of gravitational waves, gamma rays, and other electromagnetic radiation. These events are rare, but they can be detected by instruments on Earth, providing new insights into the nature of gravity, neutron stars, and the extreme conditions of the universe. Neutron stars exhibit intense gravitational fields, much stronger than those found in normal stars. The gravity on the surface of a neutron star is about 100 billion times stronger than Earth's gravity, meaning that an object would be crushed under its own weight almost instantly if it were placed there. This gravity is so strong that it bends the path of light around the star, creating a phenomenon known as gravitational lensing, which I've covered before, and if you'll recall, it allows observers to see parts of the star that would otherwise be hidden. One of the most intriguing aspects of neutron stars is their interaction with their surroundings. Neutron stars often form in environments rich with material left over from the supernova explosion that created them. As a result, they can accrete material from their surroundings, gaining mass and angular momentum in the process. This accretion can lead to the formation of an accretion disk around the neutron star, where material spirals inward before eventually falling into the star's surface. The energy released in this process can power intense X-ray and gamma ray emissions, making neutron stars some of the brightest objects in the universe at these wavelengths. Neutron stars also play a key role in the synthesis of heavy elements in the universe. When two neutron stars collide in a binary system, the tremendous energy released can create conditions suitable for the formation of heavy elements such as gold and platinum. These elements are then scattered into space, where they can become particles processes of cosmic evolution. Neutron stars are the remnants of massive star deaths, compact objects composed mostly of neutrons that exhibit some of the most extreme properties in the universe. Their formation in supernova explosions, coupled with their immense density, pressure, and magnetic fields, make them a key subject of study in astrophysics. Neutron stars also emit radiation across the electromagnetic spectrum, with pulsars being a particularly important subset. Their rapid rotation, incredible gravitational fields, and interactions in binary systems contribute to our understanding of fundamental physics